Okay, we are live now. Okay, I suggest we start. So, hello, welcome to all. This is another edition of the One World YoungStatS webinar series. Today, it is the first webinar in the springtime. For others follow, but we will announce this probably at the end of the seminar. Today, we will speak about selection of priors in Bayesian structural equation modeling. This part relates also to a conference about a month back in Tilburg. So to shortly introduce the topic, structural equation modeling is an important framework within the social sciences that encompasses a wide variety of statistical models. Traditionally, estimation of SEMs has relied on maximum likelihood, but this leads to a variety of situations in which the maximum likelihood performs subpar. This led researchers to turn to alternative estimation methods, in particular Bayesian estimation. However, currently it is unclear how to specify the prior distribution in order to attain the advantages of Bayesian approaches. And today we will try to discuss some of the aspects of this appropriate prior distribution. The speakers for today are Miočević of McGill University, Canada, Sonja, the Winter University of Missouri, United States, and Mauricio Garnier-Villarreal from Vrije University, Amsterdam, the Netherlands. Discussant for today's webinar will be Sarah van Erp, one of the organizers of the conference in Tilburg, who is resided in Utrecht University, the Netherlands. I also note, please put your questions in the chat. They will be asked, we try to ask them in the meantime or following the presentations in an open debate, and the webinar is recorded and it is put on YouTube. So without further ado, I give the word to Milica, please, for your presentation.
Hi, everybody. Thank you, Andre, for the introduction, and thank you, Sara and Andre, for the invitation. I'm really happy to be here. So I'll be talking about Bayesian methods with power prior distributions for mediation analysis. So I'll share my slides really quickly. Or maybe not so quickly. Okay, so today I'll be talking about, as I mentioned, I work on mediation analysis and Bayesian methods for enhancing mediation analysis. So I'll start my talk first by talking about what is Bayesian mediation analysis and what are some of the benefits of doing mediation analysis in the Bayesian instead of the frequentist framework. I'll talk about informative prior distributions and what we know about sources of prior information and considerations when specifying informative priors. And finally, I'll talk about how we can specify power priors and how they can enhance mediation analysis. So as most of you probably know, mediation analysis is used to investigate intermediate variables that we call mediators that transmit the effect of an independent variable on the dependent variable. So the notation I'll use M for the mediator, X for the independent variable, and Y for the dependent variable. So let's say we have an example where we're interested in studying the effects of alcohol on GPA, and specifically we're interested in seeing whether if a student attends an Alcoholics Anonymous meeting, that reduces the amount of drinking they do when they're in a social setting, and whether that has effects on their GPA. So in this model, we're interested in evaluating whether the attendance of an AA meeting versus not attending it has an indirect effect on GPA through the number of drinks consumed when drinking. So this indirect effect is computed as the product of paths A and B that we see in this figure. And we also have the direct effect of attending an AA meeting on GPA, controlling for the mediator. We'll denote this direct effect with C prime. So let's take an example data set. I found this data set online from a public database. So in my research, I don't collect my own data. And I'll link back to why this is important. So this was an example from the Harvard School of Public Health College Alcohol Study. These data were collected in 1999. And this extremely well annotated source of data collected information on students' use of alcohol, tobacco, illicit drugs, as well as some of their attitudes on campus policies, personal difficulties caused by drinking problems, and information related to their academics, such as their GPA. So there were 2 previous waves of this study also available online. One of the waves was collected in 1993. Another one was collected in 1997. In the 1999 data, we have access to over 8,000 data points from college students in the US. So when I take these data and if I fit the single mediator model, we see that the indirect effect of attending an AA meeting on GPA through the number of drinks consumed when drinking is equal to 0.03. And if we use confidence intervals from the frequentist framework obtained using the critical values from the distribution of the product, we see that those confidence limits are negative 0.01 and positive 0.07. So in the frequentist framework here, we would conclude that there's no significant indirect effect of AA on GPA through the amount of drinking. Now, if we were to do this analysis in the Bayesian framework, there are at least 2 options. So I don't discuss Bayes factors, but that's another alternative method you could use for evaluating whether there's mediation in these data. But I'll be talking about parameter estimation. And if that's the approach you're taking, you could use the method of coefficients, which involves specifying prior distributions for all parameters in your regression models for the mediator and for the outcome. Or you could use the method of covariances, which involves specifying prior distributions for the vector of means of xm and y and the covariance matrix of xm and y. So in this talk, I'll focus on the method of coefficients. So here, if that's our approach, we would have to specify prior information for 2 intercepts, I2 and I3. These are intercepts in the regression equations for the mediator and the outcome. We have 3 regression coefficients, A, C prime, and B, and 2 residual variances or residual precisions or residual standard deviations, depending on the software you're using for this analysis. So here are the non-informative priors I specified for these parameters. So normal priors for the intercepts and regression coefficients with means of 0 and variances of 1,000, and inverse gamma priors for the residual variances with both hyperparameters equal to 0.5. So when we run this analysis in the Bayesian framework, at each MC-MC draw, we simply compute the product AB, and then we have an approximation of the posterior distribution of the indirect effect. And that's what we use to make inferences. So if we look at the posterior median of this distribution, it is identical to the frequentist point estimate, and the 95% highest posterior density interval has identical limits to the 95% confidence limits in the frequentist framework. So far, numerically, we're not seeing any benefits. However, there are several features in the Bayesian framework that are advantageous relative to the frequentist framework. So just like some of the best frequentist methods, Bayesian methods easily accommodate the asymmetric distribution of the mediated effect. So similar to the bootstrap, here we have an empirical distribution of the indirect effect that we can approximate and then get the percentiles or the highest posterior density, and that's our interval for the indirect effect. One advantage of Bayesian methods relative to frequentist is the interpretation. So here we can conclude that there's 95% probability that the indirect effect lies between the 2 limits. Also, we have a straightforward way of computing functions of parameters. So as you notice, the indirect effect is already a function of 2 parameters. It's a product of coefficients A and B. We have some effect size measures for mediation analysis that also rely on products or or dividing by different parameters in the model. So for those quantities, we don't know what an appropriate reference distribution is. So in the Bayesian framework, we can simply approximate that posterior using MCMC. As you know, the Bayesian framework is also really intuitive for building on previous findings. So today's posterior can just serve as tomorrow's prior. So we have a really intuitive way for sequentially updating our knowledge. What happens often as a byproduct of that is that we get more precise findings, and we may be able to increase power to detect our effects. So what we found in simulation studies is that when we use accurate priors that contain the same amount of information as our current data set, and what I mean by that is if we have a data set of 20 participants and the prior is based on 20 participants from a historical study, we see that in certain cases that using prior information can make the difference between do we have adequate power to detect the indirect effect or not, or sometimes it can even double power. So what I'd like to show you here is on the x-axis we have sample sizes, on the y-axis we have power, and small, medium, and large effects are determined using conventions in mediation analysis. So as we see here, the turquoise and fuchsia lines are Bayesian methods with accurate informative priors. And then we have the light green line, which is the bias-corrected bootstrap. And then the dark blue line, the one with the lowest power, are normal theory confidence limits. Bayesian methods with uninformative priors are the pink line and an orange line. So to summarize these plots for you, we see that when the effect is small and we have a sample size of 200 in our current study, if we're using no prior information, our Bayesian methods are performing really similarly to some of the best frequentist methods, and those are distribution of the product and percentile bootstrap. The bias-corrected bootstrap tends to have really high power, but also elevated type 1 error rates, so that's one of the reasons it's generally not recommended. But then when we look at a sample size of 200 and a small effect, we see that using informative priors leads to a power that's almost double of what it is for best frequentist methods and Bayesian methods with uninformative priors. If we go to the right and we look at the plot for large effects, we see that at a sample size of 20, using no prior information yields power of about 0.4 to detect the indirect effect, and using accurate informative priors that are also based on only 20 participants, we have power of almost 100% to detect the indirect effect. So clearly there are benefits to using informative priors. We have the potential to really increase the power to detect the indirect effect in mediation analysis. Now in this case, there's a really straightforward source of prior information I could use to base my informative priors on. So as I mentioned, this Harvard School of Public Health alcohol study was conducted in 2 previous years, in 1997 and 1993. All of those years have data that are publicly available online, so I could just as easily download those data sets, create informative priors, and use them in my Bayesian analysis. So had I used the 1997 data, I would have ended up with over 9,000 college students. And the studies were designed exactly the same way. So I could have used the 1997 data as prior for 1999 data. So let's talk a little bit about informative prior distributions. So here, important considerations are that if we want to use prior information, it is only helpful if the priors are accurate. So in manifest variable models, we don't need informative priors for Bayesian methods to outperform frequentist methods. In mediation analysis, at least, we end up with similar statistical properties whether we use Bayesian methods with what's conventionally considered diffuse priors or frequentist methods. However, when we move to latent variable models, we need at least weakly informative priors to avoid worse statistical properties than maximum likelihood estimation. So what study found based on a survey of the simulation literature comparing frequentist and Bayesian methods is that in the latent variable framework, we may be worse off using Bayesian methods with diffuse priors than simply using maximum likelihoods. So in manifest variable models, informative priors seem to be a perk, but are not necessary, whereas with latent variables, they may actually be a necessity in order for Bayesian methods to outperform frequentist methods. So the good news is that governments, scientists, and companies are all moving in the direction of sharing their data. So we have more and more sources of available data to base our informative priors on. So for example, if the topic of interest is alcohol research, this is a completely different database. So I went and just typed in alcohol, and there were apparently 481 studies that evaluated alcohol and had publicly available data on this topic. So of course, not all of these studies will be a perfect fit for my current study. So there will be differences in measurement instruments used. There will be differences in timing of measurement and population. But among the 481 studies, surely a few could have been useful. So the next question, once we identify a relevant source of data for basing our informative priors, we need to consider, are those data or are those observations exchangeable with the observations in our current study? So if I'm trying to fit a single mediator model where X and M predict Y, one consideration is, can these previous data be considered as additional observations for my current study? So this idea initially came when my lab during my PhD was analyzing data of police officers and firefighters who went through really similar training at work to improve their health outcomes. So on one hand, the researchers who were administering the training designed the studies in exactly the same way. The measurement instruments they used were identical, but there may have been something about the two populations that would prevent us from using police officer data as prior information for firefighter data. So in other words, there might be something about the occupational culture as well as the demographic information of the participants that would have precluded data from police officers from serving as useful information, useful prior information for data from firefighters. So ideally, if we would like to consider our priors accurate, we would have to be able to consider data from a previous study as additional observations from our current study. That would mean that there are no relevant characteristics by which the populations from the two studies can be distinguished. So in this talk, I focus mostly on how to mitigate population differences between the prior information and the current study, but there are many other things that could come into play that are topics for future research. So for example, our two studies could differ based on the population the sample was drawn from. Power priors, as I'll explain, will be one solution to that. But there are other differences that could occur. So for example, study design could be different. So the manipulation that was used in an experiment, for example, or the timing of the measurements in your study. Measurement instruments and definitions of a construct could be different. So that's another obstacle to simply using historical data to construct your informative prior. So for now, let's focus on how do we mitigate differences in population, assuming identical study design and measurement instruments for X, M, and Y. So as I mentioned, power priors could offer a solution in this situation. So first, let's see what power priors are. So they were originally proposed by Ibrahim and Chen in 2000. And power priors are simply, we start to construct our power prior by first specifying a completely uninformative prior for the parameters in our model, and then updating that uninformative prior with the likelihood of the historical study raised to a certain power between 0 and 1. That updated uninformative prior yields a power prior distribution, and then that becomes our informative prior for our main analysis of interest. So the main challenge here, obviously, is how do you select this power A0 to which to raise the likelihood function of the historical study. Of course, the more exchangeable the previous and the current study are, the larger the value of A0. So if A0 is 1, that is akin to using the full informativeness of the historical data in your analysis. If A0 is equal to 0, you're completely discarding the historical data. You're not borrowing from the historical data at all. Any value between 0 and 1 should be a function of the exchangeability of the historical data and the current data. Quantifying exchangeability can be fairly challenging. So you could make a list of relevant characteristics and then see whether they match. You could ask experts on what they consider the appropriate values of A0 to be based on their beliefs about the relevance of a historical study for the current study. You could specify joint power priors wherein you don't select the value of A0 a priori, but you assign a prior for it. Or you could decide, or you could let the data decide on the value of A0 by having some metric that compares the distribution of XM and Y as well as relevant covariates in the previous study and your current study. So what my co-author and I did is we based our weight for the power prior on a comparison of covariates and relevant variables in the model between the historical data and the current data. And the measure we used for this comparison was the generalized Mahalanobis distance. So the further away the clouds of data points were between the historical study and the current study, the lower the value of A0. However, we didn't do so for the entire sample at a time, but rather we evaluated each observation from the historical data. Each observation had a Mahalanobis distance, and the A0 value for each observation was computed as the inverse of this distance of the observation from the historical data from the cloud of data from the current study. So I'll show you how this worked out in an empirical example. So the Rosetta Stone project was a study of different depression scales using data collected in the United States. So in these data, there are multiple collection sites, some were in person and some were online. So for example, we have 401 observation from Duke University. There was some data collection at Pittsburgh, at Stanford, and so on. But for our purposes, we'll focus on the data collected at Duke, as well as data collected online via polymetrics. The sample size collected at Duke was 401 observation, whereas online we had almost 20,000 observations. So as you can see, using the online data could be quite a rich source of prior information that could maybe help us increase the power to detect the indirect effect here. So if our clinical sample from Duke is considered a representative sample from the population of interest, we can use the generalized Mahalanobis distance to select points from the polymetrics online sample that could be considered as additional observations from the Duke study. So in this case, our model of interest was still a single mediator model. Here we have pain predicting restless sleep, which in turn predicts the extent to which the participants have trouble concentrating. In addition to these three variables, we used covariates sex, race, and age in our computation of the generalized Mahalanobis distance, as well as covariates in our models for the mediator and for the outcome. So relative to the current data set, the polymetrics clinical sample was less racially diverse. It was mostly male, and it was older than the Duke sample. Polymetrics had participants from the clinical population and the general population. So the clinical population had some psychological issues in the past, whereas the general population did not. And the Duke sample was a clinical population too. So you could see how we could have some concerns about the polymetric sample from the general population maybe not being able to count as additional observations from a study that only used clinical participants. So we used Bayesian methods to analyze these data. First, we analyzed the data with diffuse priors. So we simply took the 401 observation from Duke and analyzed the data with a diffuse prior. And then we used power prior distributions based on polymetrics data with individual values of A0 based on the generalized Mahalanobis distance that was computed using the three covariates I mentioned, as well as variables x, m, and y. So what we see here is, so the solid line are results from the Bayesian analysis with diffuse priors, and this is the credibility interval for the indirect effect. The dotted line here are the results using the power prior distribution. So what we saw is that power priors were based on approximately 78% of the observations from the Polymetrics general population data set and 100 observations from the Polymetrics clinical data set. So those were the percentages of observations that met the cutoff we set for the generalized Mahalanobis distance. So in other words, they were in the top 95% of the values of, the bottom 95% of the values of the generalized Mahalanobis distance. The cutoff weight A0 for inclusion in the power prior was 0.55, and the average value of A0 of included cases was 0.83. So in terms of whether this led to improvements in our analysis, we see that both diffuse priors and power priors would lead to the same conclusion with respect to whether the indirect effect is 0. So both credibility intervals exclude 0. However, when we use power priors, we see a 76% reduction in interval width. So we see a gain in precision. So in order to evaluate whether the generalized Mahalanobis distance is an appropriate metric for trying to distinguish between historical and current data, and to see how that works out with power priors, we conducted a simulation study. And here we had 3 different exchangeability scenarios. The exchangeable historical data set
Milica, I hate to interrupt, just about 2 or 3 minutes if possible.
Okay, thank you for letting me know.
Okay, thanks.
Okay. So I'll quickly tell you what are the exchangeability scenarios. So one was a perfect exchangeability. The sample is exchangeable with the current data. First type of non-exchangeability was drawn from a population that had different values of A and B. Anyhow, one non-exchangeability scenario had different values of the indirect effect, and different values of covariates, and the other non-exchangeability scenario had same values of A and B, but different distributions of covariates. So really quickly, if you look at these plots that I'm about to show you, the rows are always representing exchangeability scenario, and the columns are effect sizes, and on the x-axis we have sample sizes. So here, when we look at the 2 non-exchangeability scenarios, we see that if an observation was taken from the non-exchangeable scenario, it would have had really high weight. Whereas with the exchangeable scenario, there was differences in weights. However, in terms of proportion, in terms of whether that led to bias, we see that it didn't. So here we have a line that represents bias of 0. So for both exchangeable data and non-exchangeable data, on average, bias is 0 when we use power prior distributions and when we use diffuse priors. So in these plots, the white boxes will be non-informative priors and the gray boxes are power priors. And what we see is an increase in precision. So here we have a reduced posterior standard deviation when we have exchangeable data, as seen by the gray boxes being lower than the white boxes, whereas with non-exchangeable data, there is no borrowing. Therefore, our results are identical to results with diffuse priors. In terms of power, remember there's barely any borrowing when the data are not exchangeable. So the Mahalanobis distance was a good metric to evaluate that. So we see no gains or reduction in power with power priors with non-exchangeable data, whereas with exchangeable data, we see a gain in power when we use power priors relative to diffuse priors. So to summarize really quickly, in SEM, it's difficult to specify accurate priors due to non-exchangeability between historical and current data. So what we saw here is a method that could distinguish between whether the data are exchangeable or not. And if the data happen to be exchangeable, we can use them to specify a power prior that will increase power without introducing bias. Now, what's necessary to assume in this case is that the current sample in our current study is a representative sample of the population of interest, And relative to that sample, if we compare a historical sample, we could accurately determine whether that's an appropriate accurate prior. Now, future directions. What I have shown you today is based on a manifest variable mediation model. It'd be interesting to extend this to latent variable models, both mediation and other types of SEM. And we, of course, still need methods for creating accurate priors when other types of non-exchangeability are present. So non-exchangeability in study design and measurement instruments. So thank you very much for your attention.
Thank you a lot. It's a virtual clap, actually. Thanks a lot. I don't see any question in the chat, just a short one. At the end, you mentioned extensions to latent variable and other mediation approaches. Could you maybe shortly comment? And I had in mind in mediation, multiple mediators. I think in this analysis it was only one. Could this be immediately extended, or would any similar problems of exchangeability or other problems appear there?
So the extension to multiple mediator models, while we're still in a path analytic framework, is more straightforward because that's just another covariate to add to the Mahalanobis distance computation and just another mediator to add to the model. So that we could do tomorrow. The extension to the latent variable model is potentially a bit trickier because we're dealing with indicators, whereas our relationships of interest are between the latent variables. So there, it should be the same in principle, but I can't promise that it's going to work as well as it does for manifest variable models.
Thanks. And we will just take one additional question in the chat, and then I suggest we move forward. And Merkel asks, thanks for the talk. Could you talk about computation time of power priors versus diffuse priors? I could see power priors taking a while if the likelihood is complicated.
So these were normal likelihoods. So I guess I avoided the computational difficulties in that sense. To be honest, so here, the way we computed it is all the data were together, and then the observations from the current study just had power of A0, whereas observations from the historical data had a different value of power. So if that could lead to additional computation time, then I would imagine the power priors do need a longer runtime probably. But thinking back on the simulation study, it wasn't that computationally intensive, but again, normal likelihoods.
Okay, thanks a lot. I suggest we move forward also in the interest of time. So I give the floor now to Sonja. Again, virtual clap naturally. Thanks, Milica, for the presentation.
Yeah, thanks, Milica. That was really interesting. Definitely something I hadn't heard about before. So let me share my screen. Okay. Smaller. So yeah, I'm Sonja Winter, and I work at the Missouri Prevention Science Institute at the University of Missouri. I completed my PhD in quantitative methods at UC Merced last year, and today I'll be talking about assessing prior data disagreements in Bayesian structural equation modeling. So in the next 20 or so minutes, I will introduce the idea of prior data disagreement. I'll talk about 3 methods that we can use to assess it and discuss some results based on a simulation study that looked at these methods. And then I will just end with some conclusions and future directions. So what is prior data disagreement? The term kind of gives it away. It occurs when the priors that we specify in our analysis don't align with the information that's provided through the data that we've collected, which we express in a data likelihood distribution. So in this figure, there are different sort of ranges of agreement to disagreement. In panel A, we probably see the ideal situation. The reason why it looks like one distribution is because the prior and the data perfectly overlap. I think this is a situation we probably see a lot in simulation research looking at priors, because we know what the true values are, and so we can get these priors to be perfectly matching. A more realistic situation probably occurs in what we see in panel B. Here, the prior and the data don't perfectly align, but they still have quite a bit of overlap and seem to agree, at least in some extent, on where the parameter value is supposed to be. Then in panel C, we see what we call disagreement in location. Here, the distribution for the prior occupies a completely separate area of the x-axis compared to the data likelihood, which is one type of disagreement which I think we intuitively would think about most. But there's a second type of disagreement, which we would call disagreement in information, which is shown in panel D. Even though these two distributions are centered around the same values, we can see that the prior distribution is much more informative in that it's more narrow. And this might happen if our data likelihood is based on just a small number of observations, providing only a vague estimate of the parameter, whereas our prior information is very informative. So this can also occur the other way around, where our data is more informative than our prior. I think one situation where that happens a lot is when we use uninformative or diffuse priors in our analyses, which are usually very flat and provide very little information. So why does this matter? Why should we be looking at this? And I think a true subjective Bayesian would say that it doesn't matter, because our prior is just one piece of information which we then update with our data, and then we just collect another sample and continue the cycle. But for those of us who don't have the luxury to keep collecting more and more data, I think more pragmatic Bayesians would be interested to know that these priors that diverge from the data can result in severely biased estimates. And this bias does not necessarily disappear with samples that are considered large. So if we look at those sort of recommended sample sizes for structural equation models, many people assume that at that point, the priors don't really matter, but they can still really affect the parameter estimates. In addition, divergent priors also affect model fit indices to the extent that your correctly specified model looks misspecified. So in my research, I've so far looked at 3 different ways of assessing prior data disagreements and how those can be used in the context of structural equation modeling. Each of them answers a slightly different question. The first approach I looked at is called the data agreement criterion. And this tries to answer the question, is this prior a good representation of the information present in the data about this parameter? The second approach uses the Bayes factor, and in general, it asks, does this prior or this prior specification result in a marginal likelihood that is more supportive of the data than some other prior specification? And finally, we can use prior predictive p-values, which look at if my observed data are unexpected under this prior specification. So to look at these 3 methods, I set up a simulation study where I used this model as my population model. Some of you might recognize it as a growth curve model or latent growth model with 5 time points, y1 to y5, and an intercept and a linear slope. I chose this model specifically because it's somewhat intuitive to think about informative priors for the average intercept and average slope parameters. A lot of researchers will have some idea of where their construct of interest begins, the intercept, and how much it increases or decreases. In my study, I looked at 4 different sample sizes because, as we know, sample size affects the impact that your prior has on your results. And so it would be interesting to see if at some point it doesn't really matter if there's prior data disagreement and we don't need to detect it anymore. I set up 7 different priors for the intercept mean and for the slope mean, and then crossed those conditions to create 49 different prior specifications. Within these priors, there are 3 priors for each parameter that resulted in disagreement in location. These were called the divergent priors or diverged priors. And as you can see, they are sort of switched or moved towards the right of the population value, and they have 3 different levels of informativeness. Similarly, there are also 3 informative priors that do align with the population value, which are the priors in the green colors. However, there are also 4 priors that can result in disagreement in information for our smallest sample size of 50. And these were the 2 strongly informative priors, whether or not they aligned with the population value. And it will be interesting to see if that's something that these methods will be able to detect or not. And then finally, I also wanted to note that, as I said before, we can look at our diffuse prior as having disagreement in information as well, but we will have to see whether or not it makes a difference in this case. Before looking at the 3 methods, I wanted to make sure whether we should even be detecting prior data disagreement, because if it doesn't affect our posterior estimates, then maybe it's just too much work and we shouldn't really put our efforts into that. And so for this talk, I'm just going to focus on the relative bias in the estimates. But in my research, I also look at the posterior standard deviation and those types of things. So there's a lot of graphs here, but basically the 7 intercept priors are represented in the columns. The 7 slope priors are represented in the rows. And within each plot, we have the sample sizes on the x-axis, with each parameter represented by a line. The black line is the intercept mean and the gray line is the slope mean. And basically we see that for the 2 diverged and moderately or strongly informative prior conditions, this is where we see meaningful relative bias. And with meaningful, I mean larger than 10% change in parameter estimate on average. And what's somewhat interesting to me, at least, is that when we have these diverged and strongly informative priors, this bias doesn't necessarily disappear when we get to the largest sample size. So even for NS500, looking at prior data disagreement might still be relevant in this case. Moving on to our first method, the data agreement criterion. So, 1 second. Sure, I explain it right. So, the data agreement criterion, it has its formula and everything, but before going into that sort of technical stuff, I want to use this figure to explain how it works. The data agreement criterion, or DAC, quantifies how much information you lose when you try to approximate the data likelihood with a prior distribution. So in order to compute this value, you first start by specifying a benchmark prior, which is supposed to be a minimally informative prior, and so it should minimally affect the posterior distribution, which will mean that the posterior will be a good reflection of the information present in the data. And we see this in the top left of this figure. The sort of green dotted line represents a very flat prior, and the orange solid line represents this posterior distribution, which we also call the reference distribution. We can visualize how much information we lose when we try to approximate this posterior using our prior, which is shown in the bottom left plot. Here we can see that when we try to approximate the reference posterior using this really flat prior, we lose a lot of information because the benchmark prior places very little probability on the region that the posterior distribution is centered on. So there's a very peaked gray distribution here. The next step for computing the DAC is to now approximate the reference posterior using our own informative prior. So this is what we see in the top right part of this figure. The green dotted line is now a more informative distribution, and the orange line still stands for this reference distribution. Now, if we look at the loss of information, we see that compared to our benchmark prior, we lose much less information when we approximate this distribution with our researcher prior. So even though this prior is not in perfect alignment with this reference posterior, it's still a better approximation than using our flat prior. And so to get the DAC, basically what you do is you calculate the ratio of loss between a benchmark prior and your researcher prior. So the formula for computing this ratio is shown here with more technical notation. And to figure out how large this gray area is going to be, what the loss of information is, researchers often use something called the Kullback-Leibler divergence, which I've also included on this slide. For interpretation's sake, when you find that the DAC is larger than 1, it means that there's more loss of information if you're using a researcher specified prior, indicating that there is prior data disagreement. And then in contrast, if the DAC is smaller than 1, then it means that your researcher prior is a better approximation of your reference posterior. And so it's in agreement with your data. So this plot shows you some of the results that I found for the DAC. Overall, I found that it was likely to detect prior data disagreements when the priors diverged and were moderate or strongly informative, which were the 2 priors for which we want to find that there is disagreement. So that's great. However, something that was maybe not so great is, at least for the moderately informative priors, this detection was not as good when we had small samples compared to larger samples, even though in smaller samples it would be more important to find this disagreement. On the other hand, for very small sample sizes, as you can see towards the left-hand side of this plot, the DAC sometimes detected disagreement when the prior was aligned and strongly informative. And as you remember, that sort of represents a disagreement in information. And we can now see that the DAC is sensitive to that kind of disagreement as well, at least to some extent. Moving on to our second method, which was the Bayes factor. And I think if you're familiar with Bayesian statistics in general, you're probably more familiar with using the Bayes factor to compare different models. However, you can also use Bayes factors to compare different prior specifications, holding your data and model constant. So for assessing prior data disagreements, researchers have used a benchmark prior specification, which is similar to the DAC for comparing to our researcher specified prior. So something that's important to note here is the DAC looks at each parameter individually. So you look at one prior and one reference posterior. However, the Bayes factor looks at the model as a whole. So you have a full prior specification that needs to be the benchmark or uninformative, and then a full prior specification that represents the researcher-based priors. In general, we know that if the Bayes factor is larger than 1, it indicates more support for the benchmark priors, implying prior data disagreement. However, we also know that a Bayes factor of larger than 1 might not be convincing enough evidence. I think in the sort of guidelines, we would call that anecdotal. And so one of the questions I asked in this research was, is a Bayes factor of larger than 1, is that stringent enough, or should we look for a different type of cutoff? Actually, when I looked at the Bayes factor larger than 1, spoiler alert, it was not stringent at all. So I ended up looking at a few alternatives. So this figure is set up in the same way as the figure for a relative bias that I showed you earlier, with the priors for the intercept in the columns and for the slope in the rows. Here, each line represents a different Bayes factor cutoff. With the blue line representing a cutoff of Bayes factor larger than 3, indicating prior data disagreement. The sort of yellow-orangey line stands for a Bayes factor larger than 10, so this is slightly more stringent. And then in addition to that, I also used some ROC analyses to find a custom cutoff at each sample size level that would optimize detection of prior data disagreement, which is shown here in a red line. Overall, I think we can see that all 3 cutoffs were likely to detect prior data disagreement under the prior conditions that we are interested in, which are those diverging and moderately or strongly informative priors. In addition, we can see sort of in the top left of this figure that the Bayes factor cutoff of 3, which is the blue line, was also sensitive to detecting prior data disagreement when we were using more informative but aligned priors with smaller sample sizes. Again, this is an indication that this the Bayes factor can be used to detect disagreement in information, in addition to disagreement in location. However, something you might notice across this entire plot is that the 3 Bayes factor cutoffs were less accurate when our sample size was 500. In many of these plots, you see the line take a steep dive down towards a much lower value. So what's going on there? Basically, when you have a larger sample and you're estimating a model with a lot of parameters, your Bayes factor estimate can become unstable if you don't use enough MCMC samples to estimate it. So this is something that, in my case, was a result of the package I used to compute the Bayes factor, which uses something called bridge sampling. And in their manual, they actually say that testing different models, or different prior models in this case, requires an order of magnitude more MCMC samples than estimation. So even though your model is converged according to your R hats or effective sample sizes look good, you still need a magnitude more to get a stable Bayes factor estimate. And for my study, even using very powerful computers, if I would have had to do that for this condition, it would have taken almost a year. And this was part of my dissertation research, so I did not have time for that. However, I don't think that that means that we cannot use this method per se when we have larger samples, because if you just have your one sample, then this is just something to keep in mind. I would recommend maybe comparing several different chain lengths to see when your Bayes factor converges to a more stable estimate. Moving on to our prior predictive p-value method. So this method maybe also sounds a little bit familiar, but more in terms of posterior predictive p-values, which we can use to look at the predictive performance of our model. But the prior predictive p-value is based on the prior predictive distribution. And so to get this distribution, we look at our model and our priors, but we don't include our data in creating this prior predictive distribution. And so it's completely based on the information that we provide through our priors. To generate these samples, we start by simulating values from the model parameters, which are just based on those prior specifications. And then we use those values for the parameters to simulate random samples of our observed variables. So these samples are shown, for some example, are shown here in the bottom left. In these gray distributions, we have 9 prior predictive samples that are representing some sort of observed variable. And then to translate those into a prior predictive p-value, we compute a summary statistic for each of those samples. So for example, we think something relevant about our observed data is its mean. So we compute the mean for each of these samples, and then we create something called a prior predictive distribution, which is shown here with these light blue histogram bars. And then to get the prior predictive p-value, we basically look at how many of these sample values from the prior predictive distribution resulted in a mean that's larger than the actual mean that we observe in our data, which is shown here with the vertical blue line. In this case, when these prior predictive samples and their summary statistics are sort of evenly distributed around our actually observed mean, our prior predictive p-value will be close to 0.5, and this will indicate prior data agreement, because our priors are pretty able to estimate our means with some error on each side. However, what if our observed mean was 3 points higher and we still got these prior predictive samples based on our priors? Now we can see that most or just a few of these simulated means are larger than our observed mean. So the prior predictive p-value is now 0.004. This would indicate prior data disagreement. I don't think there are these set rules about what kind of prior predictive p-value indicates disagreement. However, I think something that people have used in the past is if this value is smaller than 0.05 or larger than 0.95, so out there in the tails, then maybe we can say that there is some prior data disagreement. So I decided to look at this approach using these cutoffs for two of the variables that were observed in my samples. Specifically, I looked at the first time point and the last time point to see how the priors affected those prior predictive samples at those 2 points. And lost my train of thought. What was I saying? Oh yes, and for my summary statistic, I decided to look at the mean of each variable. However, you can use whatever summary statistic that you think is relevant for your data. So if you are more interested in the variability at each time point, you could have gone with the standard deviation or the variance or the range, the median. Everything is possible. So again, this figure looks the same as the ones that we've seen before. But as you can tell, when we use these cutoffs of 0.05 and 0.95, we don't really detect a lot of prior data disagreements, especially not when we're looking at the first time point. So when we're looking at y1, which is shown here with a blue line, which you can barely see because it's just flat against the 0. When we looked at the final time point, y5, we do see that if both priors are diverged and informative, and our sample size is relatively large, so that's this bottom right part of the graph, we do get some detection of prior data disagreements. And intuitively, I think that makes sense because our last time point in simulating these samples, it will be more severely affected by our priors because at this point, the intercept prior loads on that if you think back to the population model diagram. And similarly, the slope also affects this time point, whereas at y1, the slope prior doesn't affect what kind of values we're simulating at all because it's the first time point, so there is no slope effect yet. It's only the, sorry, do you want to say something?
Sonja, I'm sorry to interrupt. Also, a little bit, 1 or 2 minutes, if possible.
Okay. Yeah. I'm almost there.
Thanks. Great. Thanks.
Yeah. So I decided to look at a slightly less stringent cutoff of smaller than 0.20 or larger than 0.80. And here we do see that we start to get some detection of prior data disagreement when we look at our first time point, and more when we look at our final time point. But again, it's more likely to detect this disagreement when we have larger samples compared to smaller samples. So yeah, I thought this was pretty interesting. Oh, and then something you maybe also noticed is this steep vertical uptick when we're using these diffuse priors with this large sample size, which I also thought was very strange. Like, why are we all of a sudden saying that there's disagreement here? So long story short, there's some weird computational issue, I think, with RSTEN if you're using the RSTEN package for estimating these models. If you're using diffuse priors to generate these samples based on complex models, where sometimes the prior predictive samples are just nicely spread around your observed value, but sometimes it gets stuck on some other value. And it's hard to control this behavior because in addition to like using a seed or starting values or making sure your R version is okay, the behaviors seem to change based on your operating system, hardware, all this other stuff. So it's definitely something I'm still looking at, which was kind of strange. But overall, after looking at these three methods, I came to some conclusions and future directions. I think overall, each method has its pros and cons. The DAC and the base vector both rely on a benchmark prior and figuring out non-informative priors that are a good representation of your data. It's kind of tricky. In addition, the DAC can only look at one parameter at a time, And so you can't really look at interactions between different priors. The base vector doesn't have a clear cutoff, so researchers will have to justify which cutoff they use if they use one. And the prior predictive p-value, I think there's a lot of things to play with there, but that can make it overwhelming because you have to figure out the summary statistic that you want to look at. You have to figure out which observed variables to focus on. And when we estimate structural equation modelings, you often have many observed variables, and your priors are often placed on latent factors instead of directly on some parameter that has something to do with our observed variables. So it can be difficult to think about how those priors would translate into something that we can measure in our prior predictive samples. I also thought it was kind of disappointing that the DAC and prior predictive p-values performed better with larger samples where the impact of the prior was less detrimental. And if you do find disagreement with small samples, it might indicate disagreement in location, which we saw is detrimental, or it might indicate disagreement in information, which is not necessarily bad, at least not in terms of parameter estimate bias. So my advice is probably using multiple of these methods and maybe comparing multiple of these priors. And in that sense, I think it's a valuable tool for prior sensitivity analysis. So for future directions, I really want to look at more of these methods with smaller samples. And I also want to look at assessing some sort of prior, the quality of your prior something before you collect your data. And I also want to look more into these benchmark priors when they are appropriate, if they depend on the model and all that sort of stuff. So thank you. I had fun talking about this. Any questions?
Thanks a lot. Everybody joins in the virtual clap. I don't see any question in the chat, and in the interest of time, we will definitely debate this also following Mauricio presentation. I suggest we just move now to Mauricio.
Sounds
okay. Great, thanks. So,
thank you.
Thanks.
I'm gonna diverge a little bit since I didn't. I'm gonna go back to talk about model evaluation in Bayesian SEM models, and a part that, as Sonja said, can be affected by priors. The question also is where and how. First, I'm going to talk about, in general, the Bayesian model types of evaluation outside of just SEM, and then specifically how these are applied and can be applied for global and specifically local model fit in SEM in this case. In general, a lot of Bayesian SEM model fit has been underdeveloped. We are working on it. We are trying to move ahead, but there is as I said, that when I talk about this, is that we are running against decades of research in frequentist SEM, in Bayesian SEM, so that we're trying to catch up on this. The more general metric, purely from Bayesian methods, is the posterior predictive model checks, which give us the posterior predictive p-value, very similar to the prior predictive that Sonja presented. The only difference is that this one is estimated with the posterior values. And as I said, we use as a proportion of divergence between the predicted values from the model and the observed data. A problem of this method is that it has a lot of the similar sensitivities that the p-value of the frequentist chi-square has. So it has a lot of it's very sensitive to small differences in large models, etc., and things like this. Other metrics, purely Bayesian metrics, are like the dig, wake, and glow, or as the base factor as well, but these are methods for model comparison, not for absolute model fit. Neither of them is telling me if a model is good. It can only tell me if a model is better than other models. And that also goes into the assumption that one of them has to be good in a sense, because I could have just two bad models and just one of them is less bad. So neither of these solve the issue of how good or how bad a model is in a kind of more absolute sense for this. For this, a general process that I have worked on, and I'm going to present the modification indices in this, is the posterior predictive model checks. This is a general process of evaluation of predictions from our model. So what this does is that we have an estimated model. This can be any type of Bayesian model, and we simulate the data based on our parameters, based on our estimated model. Once we have that, we can compare the simulated data with an observed statistic. So basically, very simple. Basically, the prior predictive p-value that Sonja presented is an example of this. It's just that she was simulating it on prior data instead of an estimated model. And from this process is that the posterior predictive p-value comes from. And all the software that does Bayesian SEM, like M+ or Blavan, what they do is they compute this based on the chi-square for each iteration of our model. And once we have this for a couple thousand times, we can have a proportion of how many times our data diverge, for all predictions diverge from the observed data. And this is kind of the hypothesis test. That's why it's referred as the Bayesian p-value and things like this. And as I said, the behavior is very, very similar to the p-value of the chi-square test in frequentist statistics, in frequentist SEM. Now, this is the basic use for the Bayesian p-value, right? The PPP is in the idea of comparing the chi-square, right? This overall metric. But we can also see it as a general way of estimating something at every iteration of safe parameters from my MCMC. Because here is where we can really exploit the power of MCMC estimation. That instead of having one estimated value, we have a posterior distribution of estimated values. So we can now post-estimate anything. So we can post-estimate a posterior distribution of some value of interest based on my estimated SEM model, Bayesian SEM model. And if you go back to thinking in frequentist SEM, how many things in frequentist SEM are post-estimations, right? We estimate the estimated parameters is one step, but then model fit, reliability, modification indices, Lagrange, a lot of that are post-estimations. We can do that with this process and add the uncertainty related to the MCMC process. So global fit, I'm just going to do a very quick summary of this. In SEM, right, has been, for decades, has been based on multiple indexes, most of them based on the chi-square statistics. And for this, we develop equivalent versions of these Bayesian indices, in there for Bayesian SEM. And with the added advantage that now we have a credible interval around them. So when we substitute the chi-square for the equivalent version in Bayesian SEM, we can do the posterior predictive model check logic and estimate chi-square values a bunch of times and estimate CFIs, gamma hats, TLIs, RMSEAs, and this gives us these posterior distributions of approximate fit indices based on the chi-square. In the chi-square, we needed to do an adjustment. If you want to use another metric that does not need it, like the SRMR, you can also do this as part of the SRMR, as Roy Levy suggests in one of his papers. And we can now just recompute a formula as, again, a post-calculation that can be done at every estimated safe iteration of the MCMC process. So what we learned from this is that now we can evaluate global fit and accounting for the variability related to this with a credible interval, as any of these now have a credible interval. We do recommend this to use an effect size, not as a hypothesis test of good model, bad model. It is how well they are far ahead or not. And what we learned is that this can be extended as a way of building post-realized values distributions or posterior distributions, depending on who you read. Some people don't like to call these posterior distributions. And this can be calculated as something else. Now we can recalculate anything based on our SEM models and build credible intervals around it and accounting for these variability. So now the information, the idea that we had was, how else can we take this idea and estimate the next step of model evaluation in Bayesian SEM? For us, then it was, even when you have good model fit, good overall model fit, you may have some specific problems or local misfit that is not caught. If 90% of your model properly predicts data, predicts the covariance matrix, but 10% doesn't, you may still have a good CFI because it's still overall a good model, but there is still some mishaps, some missteps here and there. So there is always good and needed in SEM to evaluate the local model fit as well. One of the recommendations for this is to look, for example, to residual correlations, but one limitation of this is that it's only telling us where the prediction problem is not telling us how to correct it or how to properly correct for this. We tried several ways of doing this, neither of them work. So what we went back to was the modification indices that are commonly used to find out which parameter, which missed parameter can be added to improve our model overall. Now, modification indices are considered a 1 minus degree of freedom Lagrange multiplier associated with the overall model, approximating what will be a likelihood ratio test between the estimated model and a model with that single parameter added into it. So this is estimating the effect of adding one parameter to the overall model possible improvement in fit. This gives us multiple metrics on how to evaluate the addition of each parameter. The most commonly used are the MI. The index itself is kind of an approximate improvement in the global fit, in this case, the chi-square, when you add the respective parameter. The EPC is the expected parameter change or point in an unstandardized metric, and the SEPC is the standardized expected parameter change. So in a standardized metric, what will the parameter be like? Usual recommendations are to take into account the three indexes, these three measures, to make a decision on when to add or not add the parameter. There are some post hoc power index information about these indices, but neither of them actually represents variability or uncertainty around the index or around the metric. So going into the Bayesian perspective, right, we have a posterior distribution of estimated parameters. We can now estimate the modification indices. Well, we could estimate the modification indices based just on the final solution for Bayesian model, but this will lead us to the same limitations of frequentist SEM, that is that we have one number to only make a decision. And as good Bayesians, we want distributions, we want intervals, we want more numbers. We always, just one number is not enough for us. So going into the posterior predictive model checks, how about if we do that? If we build posterior distributions of modification indices, and now we can look at on a range of values in which they are moving, and how could we interpret this? So what we built up was functions to write this and estimate the MI, EPC, and SEPC, and now ways to build these posterior distributions of modification indices and how can they give us more information into making these decisions. Right now, the simulation, my 20,000 something data sets are running in the cluster. So right now I'm gonna give an example. And if you have done simulation in SEM, you know that these are very, very computer intensive. So in this example, I have a basic 2-factor CFA and 4 indicators per factor, and I have 2 misparameters. So we're gonna see that this cross-loading and this residual correlation are not going to be included in my analysis model. So how well can I estimate the Bayesian modification indices can find these 0.3 and 0.3 standardized parameter estimates. So in my analysis model, right, I am missing these 2 parameters. So for this, we can use a function in Blavan already is the posterior predictive model check function that you can build up any post-estimate calculation that you want. And now we can save the MI, EPC, and SEPC for this. An added feature of the PPMC function is that it also gives us posterior predictive p-values for each estimated value. So we kind of have also a Bayesian p-value of the effect that adding a single parameter could give, if that a parameter is good enough or not. I always write still p-values in quotes. I don't like them. With Bayesian, I'm not in favor of them, but still is the wording. So the addition of this is already, again, we are going to write this into an actual Blavan function. That's the next step. But we can build a function that saves the modification indices, each modification index at a time, out of the respective model that we are running. Model fit, model evaluation, we always also want to look at the overall model. As I said, in this case, we're missing two parameters of around 0.3 standardized values, but the recommended CFI and gamma hat are still giving us good fit. I think most people, if they find this, gamma hat of 0.97, ranging from 0.96 to 0.98, and a CFI of 0.96, ranging from 0.95 to 0.98, will not blink too much and just say, it's a good enough model, probably. I am okay, and I can move forward. But we always have to look back to our local fit. We always have to see if there is some particular parts of our model that are misbehaving, and if we are catching them, and how, and where can we catch them. So when we run our posterior predictive model checks, now we also go back to the problem of we want more numbers. Now we have a lot more numbers to make sense of. So here I am sorting. I have the top 5 recommendations of model fits to check. The first one is the change in the MI. The second one is the EPC. And the third one is the SEPC. So in all of them, we see that the missed factor loading of item 1 into factor 2 is the best or the strongest one in all of them. And we can also see in the standardized version that 0.27, it's kind of close to the actual true population parameter of 0.3. And also it's covered within the credible interval of the expected change in the standardized parameter between 0.17 and 0.35. This, so also here we have the PPP. Both of these are going to be symmetric. It's just the direction that you want to look at them. So if you were to use a PP, as Sonja said, right, the 0.05 that Andres is. Should I continue?
Yeah, I think so. Perhaps he has some internet issues.
Okay. Okay. So the PPPs are going to give us this idea, right, of the 0.05. We will say that all of them, the first parameter needs to be added, or is still recommended to be added. Now we compare this to the version that frequent SEM gives us. We get for each parameter, we get the MI, EPC, and SEPC, the standardized all. Very similar values, but the problem again, we only get the one value. We don't have credible intervals, we don't have PPP, we have less information to make a decision from. Now we look at this, there is an agreement basically between both the frequentist and the Bayesian in this case on where to make the changes and how. And we see that for all of them, the information is telling us that there is something needed into adding this parameter. Another option and another interpretation that is given by this addition of information is to use the region of practical equivalence. So we can choose a meaningful minimal value that we're interested to consider. So it doesn't always have to be 0, For example, Klein, for standardized residual correlations, he recommends the 0.1. So you could say if a standardized SEPC is higher than 0.1, we can consider that a more relevant parameter. I will say to use this in comparison to the credible interval, because now it's not just the value, but we can test it if the 0.1 or your minimal relevant value, it is outside of the credible interval of the standardized predicted score, which in this case, it is telling us that it will be higher than that. So it is likely that this will have a value higher than a minimal value of standardized value of 0.1. Now the other step that you will do in this process, right, is add one parameter at a time and then re-estimate the model and if it makes theoretical sense, we don't want to just add every parameter, and see how that looks. So now that we saw that this caught the first factor loading and it gave priority to the factor loading, so that's something to be noted. We see that it does give us that the residual correlation, the missing residual correlation of 0.3 is the next most likely one. And again, if we compare with the credible intervals of the standardized, both of it's higher than the 0.1 rope, and the PPP is still telling us that there is something there to pay attention at. So you look at this, right, the interpretation with rope, we will still be interested in looking at and changing this parameter further. So let's say that now I add that parameter. How does it do when I have the correct model? So when I have the correct model, there is no clear agreement on what is the most recommended parameter. There seems to be something here, kind of, but we see the effect is very low, and the credible interval for the standardized parameter is very close to zero. It's very close to zero. If we were to be frequentist and use zero as the point of reference always, we will still say that this is statistically significant, but more from idea of a region of practical relevance, this does not cover it's including the 0.1. So we will now think twice into adding this. And also we see that there is not a clear agreement at the PPP level either. So when we have the correct model, we see that these MIs are giving me negligible changes of improvements, which is good, but also are giving me more pieces of information in which to make that decision. Now I can see credible intervals, I can see the PPP, and I can have a more informed decision instead of a single value decision process. A more fully Bayesian approach could be considered the including of all possible additional parameters with strict priors close to zero. I think still the MI could be better in the sense that I think it's faster. I think there can be estimation issues with having a lot of parameters with strict priors. Also, it's very easy to cheat in the model fit. If you just add a bunch of cross loadings with priors close to zero, your CFIs and gamma hats are always gonna go up. So it's also a way to keep us honest, to not add a lot of parameters that may not be meaningful at the end. And as I said, with this, the idea is that now we can make decisions about what modifications we can make to the model with more information. Now we have the estimated MI is EPC and SEPC, respective credible intervals, PPPs, and rope versions for this. And this is a demonstration of the power of the posterior predictive model checks that we can now estimate a lot of things that we can consider relevant, a lot of post-estimation things that we do in Bayesian SEM. What else could we do? What else can we just evaluate in this form? The next step, we are running a simulation with random sample size, a miss factor loading, and a miss residual correlation. And following this, we are close to making public a Blavan function to make it more user-friendly, and hopefully also with good recommendations in the use and application. For the same, the disadvantage of more information is that now we have more things to make a decision from. So how do I read them? How do we do this? I don't want to just throw this into the world, but also to throw it with at least a little guidance for the users and some user-friendly functions as part of this. And I want to acknowledge and thank my two main collaborators in this project, Terence Jorgensen and Edgar Merkel, and also as part of that grant where Edgar Merkel is the PI. And in the OSF, you can find my presentations and the syntax that reproduces the results. Thank you very much.
Great, thanks a lot. Just on time, I would say. Thank you. So if I don't see any question in the chat, I suggest, in the interest of time, to just move to Sarah van Erp's discussion. Sarah, please.
Yes, I will just share my screen.
Great.
So that should be visible now for everyone?
It is, yes.
Perfect. Yes. So, yeah, thank you for these three really nice presentations. I think it's always amazing to see all the work that's being done in Bayesian structural equation modeling, which is obviously something that lies very close to my heart. So it's always interesting to hear all these developments. And well, I have specific questions for each of you actually based on your presentations and your slides. But I also have a more general question that I am very curious to hear what you think about this, because I have the feeling that Bayesian SEM has been moving from this kind of being a pragmatic tool where users would have this model that would be very complicated and they wouldn't be able to fit it. So then they would go to M+ and they would say estimator is Bayes, and then the model would fit. And they would be, oh yes, my model fits now. I've used this Bayesian estimation tool, so that's great. And they would kind of stop there. But recently I feel that we're moving, and I think the presentations that you gave also illustrate that, we're moving more towards, well, what I would call real Bayesian SEM, in the sense that we're actually using the Bayesian framework in a way that we're using this prior information, and we're using the tools like the full posterior distributions that Mauricio talked about as well, in a way to actually be advantageous for us. And that is kind of, I'm very curious to hear your opinions, and I have some ideas based on the presentations you gave, but your opinion as to, do you feel like this is a necessary shift to move from using Bayesian SEM as a pragmatic tool, that we really need to move into this more real Bayesian SEM, using these informative priors, becoming more subjective as well, in a sense? And if you feel like this is a necessary shift, then do you have any thoughts on how we can accomplish this, and how can we get, because we're here with a lot of people interested in Bayesian SEM, but how can we get all the applied users to actually use the real Bayesian SEM toolbox? So that is kind of my first basic general question for all of you. But as I mentioned, I also have very specific questions. So first for Milica. So I think it was very, very nice to see your presentation on informative priors, because I feel like people are always saying, oh, an advantage of Bayes is that you can use prior information. And then they kind of stop there, which is, they just say that it's an advantage, but it's not really done that much. Also, because I think it's very difficult to actually use this prior information in a correct way. And I think that is also what you have shown. So a few questions and thoughts I had during your presentation. So one thing that I'm very interested in is a more complicated situation where we have multiple mediators and we have various studies that inform various effects. So let's say we have one study that says something about 1A path for one mediator, but then we have another study that is saying something about 3 mediators in our model, and then another study that is saying something about 2 other mediators. How can we, and can we incorporate all this information, for example, using the power priors or with other approaches? So how would this translate to more complex situations? So that is the first question that I had. And then the second question, I was very interested because I was not very familiar with the power prior approach. And so I was not very familiar with these different ways that you mentioned to select the A0 parameter. And I was just wondering, because you used the last method, but could you give a bit more information also on these other two methods? So the prior elicitation and also the putting a prior on that parameter, and in which cases you would use which approach. And kind of related to that question, and later I can show this slide again, just so that everyone has to remember what I'm, like all the comments that I had. But the focus was a lot of the exchangeability of the historical data, but I can also imagine that you want to take the general quality of the data into account. So for example, is there missing data? How is the sampling, which sampling approach was taken? Are there errors in the data that you might know about? Is there a way to include this kind of information as well into this power prior? And perhaps that might also be related to the way you select A0, because I can kind of imagine that with expert elicitation, you might be able to include this, but if you use either a prior or you use the weights based on the covariates and the variables in the mediation model, then you're kind of only using the data at hand and not any alternative information. So that was a third question that I had about that. So I'm very curious to hear your thoughts about that. But before that, I will continue to the questions that I had for Sonja. Because, well, thank you for that very enlightening talk on the prior data disagreement measures in Bayesian SEM, because I think these measures are so important to also understand the priors better, especially given what we've seen, how complicated it can be to actually correctly specify these informative priors. So I think that would be very helpful to practical users. And you mentioned at one point that, okay, the true subjective base would say, hey, if there's prior data disagreement, I don't really care, I just collect more data. But then I was thinking, given that it's so difficult to actually correctly specify this prior, can we ever really trust it, even if we're this subjective Bayesian? Is it ever? Well, I'm just curious what your thoughts on are. If there are actually good ways to come up with this informative prior that you can actually take that stance of, okay, there's prior data disagreement, but I don't care, I stand by my prior. Can we ever really do that? So that was the first question that I had. And then the second question is more of a practical nature, and I think you touched upon this. But I think especially in Bayesian SEM, where you have a lot of different parameters, how do you go about quantifying this prior data disagreement in a feasible way? Also, again, for practical users. So something I'm not really sure about, is there like software available for these different measures that you mentioned? And would it also be even needed to look into the prior data disagreement for all of the parameters in your model? Or could you say, well, I'm only focusing on this parameter for the structural regression coefficient, where I've used this very informative prior, for example? And then related to that, because you mentioned these cutoffs of these different measures, but can we also interpret these measures in a more intuitive way, that we get kind of an idea of not, okay, if it's smaller than one or larger than one, then there's prior disagreement, yes or no, but also more how much prior data disagreement would there be? So that's more some thoughts and ideas on the practical side of the method. And then finally, I was also wondering how this would work with multivariate priors. So if you have a multivariate normal prior. And then, so those were the questions and thoughts I had for Sonja. And then finally for Mauricio. And I think, well, again, this work is so important just to make Bayesian SEM more useful for the applied user, because I think now we have so many tools coming from the frequentist SEM framework that people are used to, and they want these local and global fit indices. And well, you're making them available so that there's actually no excuse anymore for applied users to not use Bayesian SEM, because they can kind of use everything they're used to, but in a better way, I would say. So I think that's really great to see. And then you touched upon this subject of that you can also use these kind of small variance priors for all the parameters instead of these modification indices. And I think that is a really interesting topic because, well, as you might know, that is something that I'm working on a lot. So using these kind of shrinkage priors to kind of automatically figure out which cross-loadings or other parameters should be in the model. And you mentioned that you were not really a fan of that approach. So I'm kind of wondering, how do you see, well, let me start by the way that I see it. In my opinion, you start from this very exploratory approach where you don't really have, your theory is not there yet to really come up with this very confirmatory model. And then you could use this kind of shrinkage priors to kind of automatically come up with this confirmatory model that you could then take to a new sample. And then once you use the more confirmatory approach, then you might use these modification indices to kind of free like the remaining one or two parameters that are still in there, also based on the theory. And I'm just wondering if that would be something that you would view these kind of shrinkage priors in this regularized SEM as being useful in that situation, or whether you would always recommend to use the local fit indices to kind of free these different parameters. So that's the first question that I had. And then the second question, because obviously this whole webinar is about prior selection, I was wondering to what extent are both these global and local fit indices influenced by the prior use, because you can kind of see the prior as part of your model as well. And these indices are, well, telling you how well your data fits to the model. So I can imagine they are being influenced by that as well. And then as a final question, we kind of have everything now for Bayesian SEM, right? We have the local fit indices, we have the global fit indices. What do you think is still missing from Bayesian SEM? Or in other words, what will be the next thing that you will be working on? So those were kind of my questions for the different speakers. And I don't know, Andre, what would be do you want to go by order, or do you want to reverse order now?
We could agree, thank you for the discussion, but I suggest maybe indeed if we go in order of the speakers and each one responds if he or she wishes naturally. Milica, maybe. Thank you for the discussion. Yeah, also naturally.
Thank you for the discussion, Sarah. Could we go back to my slide, please?
Yes.
So I'll answer these first, and then I'd like to comment on the more general questions too. So the question of multiple mediators came up already in the talk. So if we have this perfect match between what data were collected in the historical study and the current study, it's very simple. It's just a matter of including another variable in the model. But you ask a really interesting question about what happens when we have very different formats in which the data are available and quite a bit of missing information. So there, I would go back to not working with regression coefficients necessarily, but going back to the summary statistics. So going back to the covariance matrix and vector of means. And I think that's a really interesting methodological challenge where one of my hopes for the next few years is to figure out what do we do when we have pieces of information in different formats. So some covariances, some means, and then regression coefficients, because all of those are functions of each other. So we just need to go back to a simpler metric and then specify informative priors that way. So here I'm thinking back to Mike Chung's work on meta SEM. I think that's one promising venue to put everything on the same metric, and then if you need a prior for a regression coefficient, you simply derive it from your covariance matrix. But that, of course, will be easier said than done. So I think that's work for the next few years. Thinking on how do we select A0 so here, the idea behind using the generalized Mahalanobis distance is we like to remove researcher subjectivity as much as possible from this choice of prior distribution. So in expert elicitation, we're all human, there might be some bias, whereas here, the only assumption you need to make is that you have a representative sample from your population, and the only space where subjectivity could enter is how you choose your covariates. So that, again, needs to be transparent when you're specifying the power prior. So that's something that reviewers could critique, and that is open for debate. So that's the only source of subjectivity in the current approach. But then would it be useful to have some expert opinion on whether the data are of the same quality? I would guess yes. So situations where I have applied power priors generally didn't run into these issues. So these are demographic variables, so we don't really have a way of knowing are people underreporting things or not reporting them accurately. But I could see this coming up in, for example, EEG studies or more complicated data formats. And can the power prior remedy this issue? I assume it would have to be a pre-processing step. So it would have to be a decision made on the part of the researcher to maybe not even use that data set or extract only the variables that are measured with the same quality as the variables in the current study. So there, I think it would have to depend on what is the issue with the data. Missing data alone with valid measures, I don't think that should be a problem, but then measures that are poorer than measures in the current study, again, is this a worse scale? Can we just adjust the reliability, or really is this measure completely going to mess with our analysis and we shouldn't even include that variable? So I think that will probably have to be handled on a case by case basis. But the power prior, I don't see it necessarily as a solution here. So there, I would think maybe if reliability can be adjusted, that's one approach. If we have completely different items, but for the same underlying construct, maybe we could use something like factor score estimation approach to put everything on the same metric and then specify our power prior. So I think there's a lot of interesting methodological work we'd still need to do to use power priors more effectively.
Thanks. Maybe also Sonja.
Yeah, can we move back to my slide?
Of course.
Thank you. And thank you for thinking so deeply about all of our talks. It's always fun to engage in these discussions, I think. So you spoke a lot about the difficulty that I think many researchers experience in specifying informative priors and where can they start, and your question ended up with, can we ever really trust them? And I think this is one thing I didn't really bring up during my talk, but when you find disagreement between your prior and your data, it doesn't necessarily mean that your prior is in the wrong, right? Like it could be that your sample is just weird or unusual, not representative, or it could be that something went wrong in your research design. And so I think in that sense, we can't really trust any part of our research, and that wouldn't be very productive. So I think we have to trust, at least to some extent, the priors, because we're not just pulling informative priors out of thin air, and that's why it's so difficult to specify them, because we have to think about them a lot and figure out what historical information we can use to inform those priors, and whether previous research is really matching our current studies. And I think in all of that, as with all parts of our research, it's so important to justify all these decisions that we're making. And I think that will go a long way in also sort of reducing people's criticism of subjectivity in Bayesian methods, because specifying a prior is just one more decision that we're making, and most of those decisions can be seen as pretty subjective, even if they're not Bayes. So yeah, I don't know. I think we can trust informative priors. And talking about quantifying prior data disagreement with many parameters and how that's practical or not, I agree that that's definitely something I've been thinking about. And I think Mauricio also touched on this with his new approach and trying to implement it in a user-friendly way, but also a way in which people might not be tempted to misuse the information that they get out of this new information. Or yeah, it's definitely something I'm thinking about a lot. When I did this research, there's not really a package where you just put in your priors and your data and everything, and then you get these DACs or these space vectors. It's all very handwritten right now, all this code. And I think a next step that would be interesting would definitely to make it more user-friendly or for general use. I could see, for example, the DAC especially is computationally incredibly simple to calculate. And so that would be an easy thing to sort of link up with Blavan output, for example, where you could just get a number for each parameter where it's compared to some benchmark prior. But then, of course, the difficulty is what are the benchmark priors you're going to use? And I think for some parameters like intercepts, it's pretty easy to think, oh, I'll just do a normal prior with a very large variance. But I think this also other research always shows that these residual variance priors, for example, the inverse gammas or the gammas or all the other distributions that people use these days, it's a little bit more difficult to figure out what would be a good benchmark. And that's definitely something I want to spend more time thinking about and working on and making this more user-friendly, because I think at least being aware that there is some discrepancy between what your prior is implying and what your data is giving you is so important. And I think it could be such a valuable tool in making a prior sensitivity analysis more systematic. Yeah. So I'm excited to keep working on that for sure. And then multivariate priors, I would say yes, these methods can handle multivariate priors. I'm not quite sure with the DAC. You might have to switch to a different way of computing the loss of information, so that the gray plot in my presentation, since it's multivariate, and I'm not sure if the Kuhlbach-Liebler divergence can really be used for that. But if someone knows that it can be, I will be stand corrected. I think the Bayes vector and prior predictive checking methods, they don't really require any specific type of prior, so they could be applied in any situation. It might be more difficult to understand where the disagreement occurs if you're working with these multivariate distributions. And I think in that case, maybe visualization would become very powerful in helping understand what the disagreement actually looks like. So yeah, I hope that was insightful.
Yes, definitely. Thanks.
Thank you, maybe Mauricio.
I'm going to start with the general question first. I still have found useful the practical Bayesians, or I call it also apologetic Bayesians, as a way of bringing them into Bayesian. So I have brought people as, well, you can do it here. They get a couple of papers, start getting these things, and then they get rolling into it. So at least as the first carrot into getting into Bayesian, I found it useful. But I still think that there is that step into real Bayesian. The biggest thing that I have found teaching the courses, especially that swings people over, is when you have this added information, added something. Because when it is like, oh, you can get model estimate. Well, I can get the other one. The inference part, most people don't care too much, honestly. Like the practical, most students are like, I can still misinterpret the confidence interval. They're okay with it. So it's kind of the notion of what is extra that can be added. So that's why, like, how present is like added information. You can have more information or modification indices I can have credible interval of this. I can evaluate more details with like the prior sensitivity, like specific parts of the model where they break. So that's how I found like better way of convincing people of a need of the Bayesian part. But still there's some people that are never gonna be converted. So, but at least that's how my selling points have worked in the last couple of years. On the specific questions, I know, yeah, you work a lot more in the shrinked priors and these models than I do. My still preference of the other approach is more practical than anything, because when I have done something similar of having like a bunch of priors to a bunch of cross loadings and parameters like this, when you have like 2 track factors, it's probably okay. You're probably going to have very few issues, if any. But when I have 5 factors, 10 factors, 50 items, so many possible residual correlations, cross loadings, either the models can take very long to converge when they have so many added factors, or there can be some identification issues on how strict the priors are or not. And the other is that something that I'm not sure if it's better or worse. And this also comes down, like even when teaching regression, right? What is better, to build up or to tear down? The modification in this approach is to build up. It's from the model that I have, adding 1 parameter at a time, what it is. The shrinkage approach is from everything that I have, how do I turn it out? Which one gives you that better model? I am not sure. Does one of them give you a better or not? I'm not sure if there is a meaningful difference in that. But for me, the other is more in the practical side of we seeing that some of these models can be hard to converge in the models that I see most people interested in SEM, right? You have 5, 10, 15 factors. So I do see a practical problem there. The prior effects, that's a good question. I think that Sonja and Sara De Pauli just got a paper on the effect on the overall fit indices, right? By the way, I couldn't find it. If you can email it to me, I will appreciate it.
Oh yeah, for sure. The priors definitely affect the global fit indices, the RMSEA and all those things, and also the posterior predictive p-value. And at least what I found interesting in my study is that if you have these sort of accurate priors, so they're agreeing in location, it doesn't help the fit. Like that doesn't really change anything. But if your prior moves, so it's shifted in location, then it definitely makes your model look like it's the wrong model, even though you're estimating the right one. So it's definitely sort of detrimental to fit, but not beneficial to fit in some way, these informative priors.
So the location is more important than the width in your results.
Yeah, exactly.
There's one of that, like I was just thinking that I don't have that condition in my modification index. I will actually, since Sonja had that, I will kind of maybe add a couple of her prior conditions. I think it's helpful to have similar simulation conditions across papers. So I could add some of the prior conditions and see how the modification indices are affected. I'm still just running things, so I can totally like add one or 2 conditions like that. And the other in what is still missing, I still have a lot in things like one specifically to priors is the simulation-based calibration. It's a very, very computer-intensive approach that evaluates priors against a model with no data at all. So it sounds something similar to what Sonja was kind of wanting a way to evaluate priors even before collecting data. I am now building up into how to make it work with Blavin. A problem is that it's very, very, I have to run the model 300 times. So it's the computer intensive part of it is very, very unpractical. So I'm first trying to have it working and then see how can it be practical with SEM models, because it has shown to be practical with smaller Bayesian models. This is from the Bayesian side, but some of these models, right, a simple regression still can run in 2-3 minutes in Bayesian. So in Blavin, we still don't have that speed. So that's something that I'm trying to see how to adjust the functionality with a practicality of having of being able to use without taking a week. I am not satisfied with the research on model comparison in Bayesian SEM. I feel that there is still a lot of it that I'm not satisfied on recommendations or all the metrics that they have used for it. In general, also, I do not like the base factor for Bayesian SEM. I feel that it's a type of metric that is so affected by multidimensionality and priors that in the case of these huge models, making it the criticisms on the requirements for it to make it stable, I feel that it needs so much work to make it a stable comparison metric in SEM that I'm going to be crucified in Amsterdam if I say this. So many base factor people are here, but I just don't like it. I feel that I prefer the wake or the low in general. So I'm not one of the next ones is to do like a general model comparison in different ways with the different metrics. And also, since we have the approximate fit indices, we can use those also because they do go into comparing CFIs or gamma hat or RMSEAs between models. So I'm trying to do like different ways, and an advantage of this is that we can actually have a posterior distribution of the difference in CFIs, for example. So this can give us a very good idea of the magnitude of difference between these models. Other thing that I have only seen David Kaplan working, but more in path analysis than in SEM with factors, is Bayesian model averaging. I feel that this is very powerful, especially for model structure, but once you include possible factorial structures, it gets very complicated. What does the model means at the factorial structure part? But it could be very useful maybe at the regression between factors part. But Blavan just now this year included the categorical items. So now we're going to be doing a lot of simulation and testing and adding features, and now with that, so that's something also that we will be adding in ANS. And for example, one of the things we found out that the fit indices don't work well with that. So now we need to adjust the overall fit indices with categorical indicators. How do we adjust now these features to the other characteristics? And something that I was thinking, especially in the framework of prior selection, and we talk prior sensitivity, and Sonja mentioned that is not very straightforward right now. I feel that everybody's just doing prior sensitivity however they think is good. They throw a couple of different priors and then they see. So I have been thinking on having like a Laban function that picks your two models with different priors and summarize the comparison between models in a couple of ways. So we can have like the difference between point estimates. We can have difference between the low bound and high bound of the credible intervals. And we can have like a base plot across the two models comparing the point estimate and intervals. So I was thinking like things like this could be added. That will not be a paper, but that will be like a very nice functionality on put two models and get like a summary of changes in the model according to this. So those are things that I have thought about, and I'm in the process of academic life.
Thank you.
Okay, thanks a lot. I open now debate to the general public. If there is any question, feel free to unmute yourself or write it in the chat. Maybe I start myself with two questions. Firstly, for Sonja. It relates to the more general question that I will ask. Sonja, you were using Kullback-Leibler divergence to measure this data prior discrepancy, one could say. What came to my mind is that in Bayesians, I think there are multiple divergence measures used, for example, Braidman divergence measures and others. Wasserstein, but this is used more for the non-parametric part. Could this be of any additional use, or maybe, yeah, what did you choose, KL?
So yeah, you're absolutely right that we could use many other divergence measures. And actually, Kimberly Leck and Rens van der Schoot, they did a study together just comparing all these different divergence measures specifically for computing the DAC or some version of it. And in their research, they found that in general, the KL divergence was the best performing one. And so that's why I decided to go with that one. But I can definitely see, depending on the situation, you might want to use a different divergence for sure. Yeah.
Maybe a second question, but I hope the others will also respond. Do not leave yet, unless you must. Basically, the last question that Sarah asked Mauricio was about the general Bayesian approaches and so on. To my impression, I also closely follow the Bayesian circles and so on. There are quite a lot of approaches like non-parametric place, like Bayesian computational approaches, inlines discussed today a lot, approximate Bayesian computation and so on. Mauricio briefly touched the computational issues. What is missing also, like Sarah asked, in SEM in this aspect, because it seems that certain, I would say, really developing things in Bayes are still rather seldom represented. While I know that there are Bayesian semi-parametric approaches to SEM and similar, which we did even, I think, talk Young, Dunson, and Baird and others. What do you think? All included. Sarah knows that we briefly, I think, touched this at the end of the Tilburg conference as well.
May I?
Of course.
Well, I have seen some people develop some semi-parametric approaches. Some people in Belgium have worked some of these models. I feel that one of the disadvantages on that is, as Sonja mentioned, is that then a lot of this is your own code. So we have JAX or STAN, and we can write our own models, and I can write my own semi-parametric or non-parametric factor model in STAN. But the difficulty is this, making it user-friendly and accessible, because as soon as you want to add one more variable, is not a small change in this code most of the time. So that's where it's, I think, is the little play between flexibility and user-friendliness of that. So that's where Blavan plays with this of having a lot of flexibility in a lot of things, but for example, it's still limited in some types of priors that you can use. So here is, and there is a code, a computational reason for that. It's just, again, it goes into how to play and where can things be added for this. So I feel that here is the difficulty for me is, right, how can we make many of these accessible without being, here is my code, go and modify it, because nobody's gonna do that. Not even I want to do that for my own code. So I feel that that's like where now Blavan, M+, or others having options helps, but all of them are gonna have limitations on these flexibilities. And I'm not sure how easy it is to make some of these, like the version of extendable and more user-friendly approach.
I think Milica, yes.
Thank you. So I just wanted to add a little bit to what are some of the obstacles to applied users adopting Bayesian SEM and making the switch. What I've noticed when teaching these methods is we don't have cutoffs for when a model fits well. And I noticed that's really concerning to applied users, but also we don't have concrete advice about what to do when the fit indices disagree. So I just think we need a lot more literature on what do you do when it's really unclear whether this is a well-fitting model. So we have a bit more of that for frequentist SEM than we do for Bayesian. So hopefully more will come in the next years.
Thanks.
Can I just add to that, to actually both what Mauricio and Milica were saying? Because I think the issue is also that, well, SEM is already quite complex and quite difficult, especially when you're moving into semi-parametric models and I don't know what kind of complex things people are doing. And then you're adding in the Bayesian component that people are not very familiar with. And you add all this added difficulty of you need to specify the priors, you need to check those. And as Milica also mentioned, you don't really have these.
Sarah, we don't hear you. Oh, It's okay now. It's better now.
Yes?
Yes.
Ah, perfect. Oh, I think, yeah, my headphones are gone. So I think that can make it very tricky for applied users, and that is where the easy to use software like Lavaan comes in. But to really encompass all the complex models in this kind of package can be very tricky and very difficult, I think. We should not underestimate that.
But maybe if I continue, where do you see this complexity in terms of SEM? Naturally, there are latent variables, but of course, all of those approaches are used also for dynamic stochastic general equilibrium models, if you wish. Where would be this obstacle? Maybe.
So I think one main obstacle is already in just a number of parameters. I mean, you have so many parameters that you have to think about the priors, and you have to think about how would you do a prior sensitivity check. It can be computationally inefficient. So I think that can make it very tricky. Apart from the whole, just building the model can already be quite tricky, right? And coming up with a good model and then comparing different models. Well, I think Mauricio also mentioned it. He's not very happy yet with the state of model comparisons in Bayesian SEM. So I just think we still need a long way. We have a long way to go still in Bayesian SEM to get it to the level of frequent SEM, which is exciting because that means there's so much work to do for us, right?
I just shortly add before Mauricio enters, I also asked this question because I was hoping, I think that quite a lot of patients followed YoungStatS. In general, we will have another patient webinar in June, and I was hoping that also this webinar will raise interest in them to maybe start working or join, I would say, the work to develop also the things here, like the people from ISBA and in the circles that I mentioned, non-parametric and other stuff. I'm sorry, Mauricio, please.
I will say that another of the problems, and this relates also to what Milica was saying and Sarah, of these cutoffs, for example, and things like this, is where they come from. Because, right, students are still, right, taught that p-value 0.05, like very, very strict cutoffs from their first bachelor class forward. So when we tell them, oh, that doesn't exist anymore, they are very decompensated. So that's why I like, for example, to use the book of Richard McGill, Rethinking Statistics, as one of the best introductions for it, because he takes the approach of, I'm going to reteach you statistics, forgetting that you even had a p-value before. And it's also the kind of the idea that if we were to teach people Bayesian from the get-go, and then we move them to Bayesian SEM, there wouldn't be that much of a problem. But because people are coming from the P of 0.05, P of 0.01, whatever cutoffs back and forth, then they're looking for the same. So I feel that here is the problem, that now we're fighting against the current, against what is commonly done, and now we have to de-wash their brain or whatever. So I think that's like a complexity of telling them, forget about that. I'm going to try to teach you without thinking about that, but they're still going to have the 0.05 there. So the 0.05 is always there. So I feel that that's one of the hardest things, is to reteach, to not care about the 0.05, to not think as a 0.05 moving to Bayesian. But it's very hard to teach that and to tell them to forget that part.
I don't think we will ever get rid of the 0.05, to be honest.
Okay, any further question from the public, from anybody? If not, thank you to all the speakers, to excellent discussion from Sarah, to all the participants for your questions. The video was recorded, it will be put online today or tomorrow. Next webinar, we will relate slightly to this. We will go into machine learning and causal inference with theory and methods for inference in multi-armed bandits on May 11th. I noted in the chat there is another Bayesian webinar or approximate Bayesian inference with Julien Arbel in June 15th, possibly related to this. So thank you to all again. Yeah, hoping to see you soon on another event on these topics.
Thank you so much for
Thanks. Thank you.
Thank you.
Thanks to all.
Thank you.
Bye.